Hey guys, it's Miss Johnson, and I'm here to bring you finally, the last part to section 3.2. Today we're talking about the regression to the mean. So we're still in LSRL. We're still talking about that least squares regression line, but we're going to talk about just kind of wrap it up today. That's really what we're getting at. So here's our two things of learning targets that we've been looking at all throughout all four pieces of this section. And today we're going to get into the regression of the mean and also like just convenient ways to write that LSRL and things like that. So a couple of things that they wanted to point out to you is the fact that you're going to see different types of computer outputs when you take your AP exam. It's not always that they will show you, and in fact, I don't know if I've ever seen them show a calculator, like a TI-84 screen view of your summary statistics. They're always going to give you summary statistics based on some computer program. So one that you see quite often is this mini tab. There's a program called mini tab, and what it will do is it will spit out to you the constant of the equation, and then it'll also spit out to you the slope of the equation, and the slope will be written next to the x variable. So if you think back to that Ford F-150 example that we've been talking about this whole time, the x variable was the miles driven. So that's the slope that goes with the miles driven. This constant is like your y-intercept. That 38,257 was the y-intercept, okay? The other things that you see the S value, which we talked about is the standard deviation, so that $5,740. You also see R squared, and it says R-SQ, so that's R squared, and that's that 66.4%. A lot of times you're gonna look at something like this, and the question may say something along the lines of, what's the R value? Well, you would take that 0.66, and you would that's your R squared, and you would just simply take the square root of it, and that's gonna give you the R value, okay? The one thing that you do need to pay attention though is the relationship a positive or a negative relationship. In this case, the slope is negative, so then it would be a negative R value because you know your line is going down, which means you have a negative association. Another program that you see sometimes is called JUMP. They say it's JMP, but you can see here you've got your R square value, you've got the root mean square, that's your S. The standard deviation is also called the root mean square, which is sometimes a phrase that you'll see in the AP exam. Not often, but sometimes. And then you'll see the y-intercept, and you'll see the x variable miles driven with the slope next to it. Okay, so that's just another program. I see this one a lot more often. I don't see the JUMP ones as much, but they do sometimes come up. So just to know how to kind of look through the data that you're given or the summary statistics that you're given based on the different software programs that you'll see. All right, so there is a way for us to calculate the the LSRL by hand. We talked a little bit about this when we did the regression line back in section, I think it was 3.1 even, or maybe it was the very first piece of 3.2, I don't remember. But we did the regression line, and you had the slope was that R value, the correlation coefficient, times the standard deviation of y divided by the standard deviation of x. And then the y-intercept was the mean of y minus the slope times the mean of x. So you can go through and calculate that value on your own. However, more often than not, using your calculator to find that LSRL is going to be the easiest way. Just know that there is a relationship between those two things. And these two equations right here, these are things that are given to you on the AP exam formula sheet. So if something were to happen where like you needed it for something or your calculator dies, because believe it or not, that does happen, you will be given a lot of formulas, and these are two of the formulas that you're given. It's just a question of when you get to the end of the year, can you remember what those formulas are actually for? That's the real kicker. All right, so now let's talk about regression to the mean a little bit. So we want to look at that LSRL and talk about how it is regressed from the mean of your X's and your Y's. So one thing that we discussed when we talked about regression lines, I think it was the first piece of 3.2. When we talked about regression lines, one value that's always on your LSRL is the mean of X and the mean of Y. So they have some added, they've given us that data back again. And I think this might even be different. Yeah, this is different data. This is the scatter plot that shows height versus foot length. Okay, so here's your equation, and you can see all the little black data points on there. That blue line, kind of blue tealy color, I guess green tealy color. I should probably put it in green, that might make more sense. That's your LSRL, okay? LSRL is right there. The mean of X and the mean of Y is always a point on the line. So what they did here is they added a couple of extra lines just for us to visually see what's happening with our means. So the vertical line at the mean of the foot length X, that's this. Then you have a vertical line at X plus 1 standard deviation. So this is 1 standard deviation of X away. Then here's your mean of Y, and here's 1 standard deviation away from your mean of Y. So mean of Y plus standard deviation. So what they're looking at here is how much did the Y value change with 1 standard deviation of X change. So here's the mean of X. If I go 1 standard deviation away, I'm right there. That's S of X. Okay, and that gets me to that line. Now, one would think that if I increased 1 standard deviation of X, I should have increased 1 standard deviation of Y as well, right? So that would mean that I'd have a point right here. The next point on my line should be right there, right? Well, that's not actually the case. The point on the line is a little bit underneath that. You can see it right here. So what is this distance? What is that distance, and why is it not a full standard deviation of Y? Well, it's not a full standard deviation of Y because the values are going to regress to the mean, and it's going to be based on our R, the R coefficient, okay? So it says for an increase of 1 standard deviation in the X variable, the LSRL predicts an increase of R standard deviations in the response variable. So R is going to be the amount of increase for every 1 standard deviation. That's why we say that these things regress to their mean. They're going to fall down towards their mean more than just going up by 1 standard deviation each time. So this little distance right here, this distance between what we would expect that point to be, because that's 1 standard deviation of Y away, that's how much the line regressed to the mean based on how well the data fit, okay? So it's not a perfect model. This just goes back to the fact again that it's not a perfect model. We don't get a line here that perfectly matches our data. It's going to have some regression in it, and it's going to have some error in the prediction. All right, so just a few more tips about correlation and regression and being smart about how we read these things and look at these things. One point that we want to make is correlation and regression lines only describe linear patterns. So if I am looking at this model right here and this model right here, okay, I can see actually all of these. So this is a model and this is a model. All of 4 of these models have an R coefficient of 0.816. But now check it out. Does it make sense for all of these to actually use that R correlation coefficient? This one for sure is not a linear model. That is very clearly a curved model. This one right here, this isn't going to be a function. These are in a vertical pattern. So it doesn't make sense to use correlation to describe models that are not linear. These two over here on the left-hand side, one could argue that this is a linear model and it just has a strong outlier, and that's what's pulling the correlation down. So this actually looks like a pretty good one. And this one on the top, you could say that this is a good model. I would say that that's probably linear, but if you did the residual plot, you might even see that this has a slight curve to it in some way. So it's always important to do a little bit more digging to make sure that the model is actually linear, and that's why we use those residual plots to determine if it's appropriate to even talk about correlation, because if we're not looking at a linear model, then correlation and regression don't make any sense for us. So one other thing, the next point or the next tip that we want to share is correlation and least squares regression lines are not resistant. They are fluid. They are going to make there are going to be differences. They are going to be heavily affected. I guess that's the way I want to say that. They're going to be heavily affected when you have outliers or clusters or weird things like that. If you take a look at these two plots right here, here's a whole bunch of data. I've got a cluster of all those red points. The purple points are where there's two children that fall in the same point. So they just used a purple dot to represent 2 instead of 1. And you can see the LSRL going through. Now, here I would argue is an outlier. Here I would argue is an outlier. And what happens is if you hop over to the residual plot, so come over here to the residual plot and check out those residuals. Those outliers, even that one, whatever that one is, I don't know. One of these maybe, or this one? Yeah, I don't know. I don't know what that point is, but those residuals are making a big difference in our residual plot. We don't see a whole lot of random scatter here. You see a really big cluster. There's a big cluster of data, and then you see some other things here. So I would argue that this maybe is not the most accurate way to look at this data set because of those outliers. Those outliers make the data set, make it hard to create a prediction line for that data set. So that's why we say that correlation and LSRL are not resistant. They're like standard deviation and mean. When you have an outlier in a data set with only one variable, the mean is highly affected. The median doesn't change. The median is resistant, so the median doesn't change much because it's all based on position. But the mean is not going to be resistant, which means it's going to change a lot. LSRL is the same way. LSRL, and if you think about it even deeper, LSRL is based off of means. So that should tell you that when you have outliers, your means are going to change, which means your LSRL is going to change. So it all kind of ties together. So here's another way of looking at that. They just did some other models of the same data set, but they took out some of these outliers. So without child number 18, if you look at with all 19 points, and you see that was that blue line right there. No, that wasn't the blue one. That was the tealy green one. Sorry, back up. Tealy green line right here. All 18 points, you get an R squared of 4.41, okay? When you take out child 18, you get an R squared of 0.11. When you take out child 19, you get an R squared of 0.572. All of those lines turn out to be different, okay? So you can see that those lines are changing depending on what outliers are in or out, okay? And then one point that we just want to make again, and we've said this point before, but we're going to make it again because this is a really important thing. Association between two variables does not imply causation. Just because I can say that a person's height and a person's, foot length, person's height and foot length are associated with each other in a positive way. The taller you are, the bigger your foot is, pretty much. Just because those are associated together doesn't mean that one causes the other. You growing taller doesn't necessarily make your feet grow bigger. That's not always how it works. You can't blame one on the other. You don't know that without doing more tests, without doing more analysis. Those are the things that are going to come for us in about chapter 7. We're going to do a lot of tests to try and determine if there is a cause. But association does not imply causation. So just because you can say that there's a strong association between two variables, you don't have enough to draw conclusions about the cause and effect without doing further tests. All right. that wraps up section 3.2 for us. That was a big, hefty section. There were a lot of moving parts in there. There's a lot of information and a lot of terms that we learned. So take some time to think it over, work on your practice assignments. We have one more section in chapter 3, and then we will be moving on to the next chapter. So thanks for listening, and I will catch you next time.